Welcome everyone to a classic sorting showdown. In one corner, we have the simple, neighborly bubble sort, and in the other, the methodical, decisive selection sort. Today, we're going to see how these two fundamental algorithms take on the universal challenge of creating order from pure chaos, and find out which one really comes out on top. So, let's get into it.
So, here's our game plan for today. First, we'll set the stage and define the problem. Then, we'll meet our two contenders, one by one, to see how they work. After that, it's time for the main event, a head-to-head comparison. And finally, we'll talk about why, even in a world full of super advanced tech, these simple methods are still absolutely crucial to understand.
You know, at its heart, the problem is something we all get. You've got a jumbled mess, a list of numbers, maybe some names, or just a pile of data. And your mission, should you choose to accept it, is to arrange it into a logical sequence. It's a task our brains kind of do intuitively, right? But the real question is, how do we teach a computer to do it, and to do it efficiently?
To make this real, this little list right here is going to be our test case for today's showdown. Just a simple, unsorted list of 5 numbers. Our goal is to apply a set of rules, an algorithm, to turn this chaos into the perfectly ordered list, 1, 2, 4, 5, 8. Seems easy enough. Or is it? Okay, before we bring in our algorithmic heavyweights, just take a second. How would you do it? Seriously. Would you scan for the smallest number and just stick it at the front? Or would you start shuffling things around until it kind of looked right? Your own gut instinct is probably closer to one of these algorithms than you think.
All right, let's meet our first contender, Bubble Sort. Now, I want you to think of this one as the friendly, but maybe slightly chatty neighbor. It doesn't really look at the big picture. Instead, it just focuses on who's right next to it, making a bunch of small, continuous adjustments until, eventually, the job is done.
So here's the core idea. Imagine our numbers are all people standing in a line. Bubble Sort just tells each person, hey, look at the person to your right. Are you taller? If you are, swap places. This little comparison and swap happens all the way down the line. After one full pass, guess what? The tallest person has bubbled up all the way to the end.
Let's watch it work with our list. In that first pass, you can see it making a whole series of these little neighborly swaps. Watch how the number 8 just keeps moving to the right, one step at a time, until boom, it bubbles up to its final position at the very end. The next pass does the same thing, locking the number 5 into place, and this just keeps on going, with each pass securing the next largest number until the whole list is perfectly sorted.
And now for our second contender, Selection Sort. This one, well, it has a completely different personality. This is the silent, methodical planner. It doesn't make a single move until it has scanned the entire group and found exactly what it's looking for. It's all about making one single, decisive action per pass. Its strategy is totally different. Selection Sort basically splits the list into 2 parts, a sorted section on the left, which starts empty, and an unsorted section on the right. In each pass, it scans the entire unsorted part, finds the one single smallest element, and then moves it over to the end of the sorted section. So applying this to our list, in the very first pass, the algorithm scans everything, sees that 1 is the smallest, and makes one decisive swap to move it to the front. Now the sorted section contains just the number 1. In the next pass, it completely ignores the 1, scans the rest, finds 2 is the next smallest, and hey, it's already in the right place. No swap needed. It just continues this methodical process. Scan, find the minimum, swap, until the job is done.
All right, we've met our contenders. We've seen their unique styles. Now, it's time to put them side by side and really see how their different strategies stack up in a direct showdown. Let's do this. Right here, the difference in philosophy is just crystal clear. Bubble Sort is totally local. It only cares about its immediate neighbors, which leads to this flurry of constant tiny swaps. Selection Sort, on the other hand, is global. It scans the entire remaining list to find the one perfect element, then acts with a single targeted swap. 2 very different ways of thinking about the same problem. So where does this difference actually matter in the real world? Well, Bubble Sort can be surprisingly fast if a list is already almost sorted. But Selection Sort's real superpower is when swapping is expensive. Just imagine you're not sorting numbers in a computer, but organizing giant, heavy boxes in a warehouse. Every time you have to swap 2 boxes, it takes a ton of time and energy. You'd want to minimize those swaps, right? Well, that's exactly what Selection Sort does. It's perfect for things like writing to computer memory, where every single write operation counts.
And hey,
Here's the proof right here with our little test case. Just look at this bar chart. To sort our simple list, Bubble Sort's kind of frantic neighbor-swapping approach took a total of 6 swaps. In stark contrast, Selection Sort's patient, methodical strategy got the exact same job done in just 2. I mean, that is a massive difference in efficiency, and you can see it plain as day.
Okay, so at this point, you might be thinking, this is all interesting, but wait, I've heard of much faster algorithms, like quicksort or merge sort. So why did we just spend all this time on these simpler ones? And you know what? That is a fantastic question.
And the answer is because these algorithms are the absolute fundamental building blocks of what we call computational thinking. They're like the ABCs of sorting. By really getting how they work, you're not just learning how to sort a list, you're learning how to see a problem from completely different angles. You get to witness this direct trade-off between making a bunch of simple local moves versus making one big, globally planned move. You really can't appreciate the genius of a complex algorithm until you've truly grasped the elegant simplicity of these foundations.
So, in the end, we've seen that while both of our contenders solve the problem, their efficiency really depends on the context. And that teaches us a vital lesson about problem-solving itself, which kind of leaves us with this final thought to chew on. The simplest path isn't always the fastest, but it makes you wonder, when is it the best one to take? Thanks for watching.